So, so let's start with our first session in the evening. So we have Sergio with the last talk of this period. Sergio, you can start with searches of new physics with neutrino telescopes.
Can you? Okay, it works. Okay, so this is the second talk on this exotic physics with neutrino telescopes, and yesterday I discussed a little bit some of the scenarios that one can test with a neutrino telescope with the highest energy events using the astrophysical neutrino flux in order to either learn from what is the type of source that could give rise to the events that are seen, or even to use those events, that is event spectra, to learn about or to search for possible features in different ways and learn about exotic scenarios. So as I said yesterday, I was focused on the high energy tail, about 10 TeV. And today I'm going to focus on what the neutrino telescopes, and I will basically focus on neutrino telescopes in the sense of huge Cherenkov detectors. So I won't talk about all the physics that can be done with smaller Cherenkov detectors like Super K, or even a smaller detector that we've been hearing about during these 3 days. So I will basically focus, when I mean by neutrino telescopes, I really mean like Ice Cube, Antares, Kilometer Cube Net or so. And I'll discuss the new physics that can be searched for with energies below 10 TeV or so. So at these energies, the main source of neutrinos, if not the only one, are atmospheric neutrinos. Juan Pablo in the first day already explained what these atmospheric neutrinos are. So atmospheric neutrinos are produced by cosmic rays coming into the atmosphere and getting into the atmosphere, interacting with the nucleus of the atmosphere and producing shower of particles. At low energies, these neutrinos come basically from the case of pions. And pions decay and then produce new neutrinos. Then you have the muons are also produced in pion decays, and then they later decay and produce electron and muon neutrinos or antineutrinos depending on the charge. And basically this is produced with a ratio of about 2 muon neutrinos per 1 electron neutrino. This is what happens at low energies. Actually, when we start going to slightly higher energies, this ratio of 2 to 1, which is like the naive ratio that you can read from here, and again, I think I mentioned that the other day, but whenever I mean neutrinos, unless otherwise stated, I mean neutrinos or antineutrinos, because these detectors cannot distinguish the charge of the lepton produced by them. So neutrinos or antineutrinos are, for practical purposes, from the detection point of view, the same. So this ratio of 2 to 1 of nu mu's to nu e's in atmospheric neutrinos, as we go to higher energies, starts growing up. And this is basically because as we go to higher energies, the muons start to live farther, start to live longer, so they can reach longer distances, and basically the chances or the probability for them not to decay before reaching the Earth are high. So basically you end up producing only nu mu's, or a small fraction of nu e's compared to nu mu. So the ratio of nu mu's to nu e's grows. Then at even higher energies, actually, as I said before, at lower energies, by low energies I mean GeVs, tens of GeVs, even 100 GeVs. Neutrinos are produced mainly from pion decay with these different features on the ratio of nu mu's and nu e's. At even higher energies, all neutrinos are produced, or most of the neutrinos are produced from kaon decays. and that happens at energies about something like 100 GeV or so, and this has to do with it's kind of a competition between decay rates and interaction rates, and at those energies, kaons are the dominant producers of neutrinos. If we go to even higher energies, and this is about 100 GeV or so, if we go to even higher energies, say something like 100 TeV or so, we have the production of neutrinos from tram mesons, which decay very fast. Pions and kaons, as I said, the production of neutrino and the fraction of the rates of neutrino and the relative production of neutrinos from pions or kaons depends on this fight between the competition between decay rates and interaction time. When we go to very high energy and we can produce, or the collisions can produce charm mesons decay very promptly. This is why this flux is called prompt neutrinos, and in that case, basically the flux of neutrino has the same shape as the flux of the cosmic ray, basically because these charm mesons are produced immediately decay without losing any energy, which is what happens in these cases. So I'm showing neutrinos at lower energies, basically below 100 TeV or so, have a powerless spectrum with an index which is about 3.7. So it's 2.7. The cosmic ray spectrum has an index of 2.7 plus one extra power law because of the energy losses and during the propagation in the atmosphere of pions and kaons. In the case of prompt neutrinos, as the flux is basically the same as the cosmic ray spectrum, the power law goes as e to the minus 2.7. So this is a bit like a summary of what atmospheric neutrinos are, and because this is actually what I will be discussing. This is the flux that I will be using during the rest of the talk. The good thing of atmospheric neutrinos, as also Juan Pablo mentioned in his talks, is that there is a huge range of energies and baselines. We are talking about energy between few GeV for neutrino telescopes up to energies of something like tens of TeV or so, which are relevant for this. So in Juan Pablo's talk, when he also split it, his two talks on high energy neutrinos and low energy neutrino, by low energy mean below 10 TeV, and I'm doing basically the same. So in his second talk, he discussed some of the standard searches that can be done with atmospheric neutrinos. So for instance, studying neutrino mixing parameters, so theta 2,3, delta m square 3,1, etc. You can also, he didn't mention that, but you can also study cross sections at extremely high energies, with energies in the lab of the order of the hundreds of GeVs, TeVs. You can even use these neutrinos to study the Earth density profile because of in different ways. Actually, at low energy you can use what is called neutrino oscillation tomography, because neutrino oscillations change depending on what is the density profile of the Earth. At even high energies, you can use the absorption of the neutrino flux in the Earth to study the distribution of matter in the Earth. And you can actually study the very same atmospheric neutrino flux and learn about, for instance, hadronic models, which are the major source of uncertainties in the calculation. So if we measure very well the atmospheric neutrino flux, we know from other experiments of cosmic ray experiments what is the cosmic ray primary spectrum, and we can kind of handle the uncertainties on the hadronic models much better, and that would help. So this is kind of the standard searches, which is what he discussed. He also discussed actually one type of physics which is not a standard, and I will briefly go through it, repeating some of the things he said, but just I will try to emphasize other aspect, which is searches for sterile neutrinos, which can also be done with that. Juan Pablo also mentioned that. But I will focus, except from that, I will talk about completely different things. So new physics searches with this type of flux. And again, as I did in the other talk, there are two ways. For instance, in the case of low energy searches, that we can use the atmospheric neutrino flux. On one hand, we can use, we can check if we see any feature in the signal, in the flux of neutrinos. So we use it as a signal and search for features on that signal. And or we can use it as a background if we know there is some source that could produce neutrinos with energies in the tens or hundreds of GeV, and then in that case we try to search for that signal over the well-known background of the atmospheric neutrino flux. So those are the two ways we can try to search for new physics with atmospheric neutrinos. As I repeat again, looking for the features for different features in the spectrum, or using the spectrum as a background for a new signal produced by some exotic source. Okay, so again we can show this kind of chart as in the high energy case that I saw yesterday, and we can search for effects at production, propagation, detection, and observables, energy, direction, and topology, which are the observables that neutrino telescopes have. For instance, I will here again are some examples. It's only one case per box. That doesn't mean there is only one case. That doesn't mean that some of the cases which are shown in one box don't go in some other box. Actually, they do. But I just wanted to put one in each box. So, for instance, you have here dark matter annihilations, and I try not to say dark matter decay this time because the other day I was saying dark matter annihilation all the time. I didn't talk about dark matter annihilations, but today I'll talk about dark matter annihilation a little bit. How that can be searched for in neutrino telescopes at lower energies. And this affects the production. The production mechanism is the source of new physics, and that affects the inner spectrum, the direction, the topology, track, showers. That depends on the different channels that this annihilation is happening to be on. Then we can have, for instance, propagation, also neutrino decay. We can have a Lorentz violation, or violation of the equivalence principle, or different things. We can have sterile neutrinos that would modify the topology, also in detection, and some non-standard interactions that can affect detection, even magnetic monopoles that would affect the topology that is seen in the detector. So I mean, there are many different scenarios. Obviously, there are more that I won't mention today, and there are more to fill in here. And hopefully this will be written in a review we are working on. I don't know when we will finish this, but it's quite exhaustive. Anyway, let me start. So a few slides on things that have already been discussed. Sterile neutrinos with searches of sterile neutrinos with atmospheric neutrino flux. So actually, in most of the talks, there have been some mention on this sterile neutrino. We had the talk on Borexino, we had the talk by Juan Pablo. We have, in different contexts, we've seen that this sterile neutrino showing up in different ways. And the reason is basically driven by this experiment that probably you've heard about, that is the LSND experiment that took place about 20 years ago, and that saw some anomaly on some unexpected appearance of electron neutrinos. So this is MEV energies with a distance of tens of meters, and that means that the probability, in order for that to happen, we needed an extra neutrino, or that was the simplest explanation, an extra neutrino, and that would mean that this U is the mixing matrix element. This is U-mu4, the extra fourth neutrino, and this is UE4. So this is the probability that the LSND within the context of 3+1 models, 3 light neutrinos plus 1 heavier, mostly sterile neutrino, was measured. So in order for this to be zero, as they were seeing, you see this is what they were seeing, and the zero is here. So they needed both angles to be different from zero. There have been many other surface line experiments searching for these sterile neutrinos, so far with no success, and most of them set a limit, for instance, on U-mu4. So that also constrains this, because if this is small, in the end this is going to be small. Both needs to be different from zero. So yeah, there was also the minimum experiment that was meant to be to prove or disprove the LSND result, and in the end, it seems that they are compatible in some way within each other, but still the surface line experiments tend to be incompatible with those results. Then there was, in the last year, there's been kind of a revival. I remember actually, I think it was like don't know, 12, 13 years ago, I was working a little bit on sterile neutrinos, and I was giving some conference review talks on sterile neutrinos. And it's kind of funny these days that we've heard about this gallium anomaly, that it was a 2 sigma effect. Actually, back 10, 12, 14 years ago, the gallium anomaly was on the other side of the game. So it was used as the proof that there was no LSND sterile neutrino. Now it's on the other side. So that 2 sigma anomaly that was seen in the gallium experiments is used as a confirmation or as a hint on the existence of sterile neutrinos. It's kind of funny how sociology works in here. Anyway, so there was a revival of all this thing after minimum couldn't rule out LSND or prove it, and after revelation of reactor neutrino fluxes that hinted for the existence of this extra particle, or just trying to explain how this suppression of the flux from the expectation was obtained, and that a sterile neutrino would explain it. So again, this could be pointing that there might be an sterile neutrino in the EEV scale. Yet this possibility is and as always has been, incompatible with surface line experiments, but new experiments have not ruled out this possibility. There are, as I mentioned, these neutrino fluxes determinations which are adding more confusion to the game. And again, atmospheric neutrinos are also not compatible with any oscillation into sterile neutrinos. A global feed in terms of surface line and putting everything together seems to point, it seems to prefer a little bit at the level of 2 sigma, so sterile neutrinos. And actually there is a recent paper using reactor results, and yeah, it's a long story actually. I think I could be talking about this, the whole thing. And anyway, what they conclude is that with the new results from NEOS and DAMS, it seems that the analysis of reactor neutrinos only favor still the possibility of a sterile neutrino, because there was some claim recently by the Diabe collaboration that this could be just explained by the fact that the fluxes from the different radioactive isotopes in the reactors were not completely well understood. And actually the Diabe collaboration did a fit leaving free the different contributions from the different isotopes, uranium, and then actually they concluded that the whole anomaly could be explained by uranium-235, I think, if I remember correctly. So this paper reassessed the problem, added new data, and actually they conclude that they agree with the Diabe statement, but still, when you add everything together with the new data from NEOS and DAMS, which are 2 experiments, one in Korea and the other in Russia, seems that we are back to the 2 sigma level of sterile neutrinos. Anyway, this is a long story, and I'm talking too much about the whole thing. I'm not talking about atmospheric neutrinos. So let me talk about atmospheric neutrinos and rephrase a little bit and insist a bit on the things that Juan Pablo discussed within this context the other day. So basically, the whole thing is that we have the 3 neutrino mixing. We want to explain this anomalies in the simplest way. We add an extra neutrino, so we make the mixing matrix a little bit more complicated. And there are, in this scenario, there are 6 extra parameters, 1 extra delta M square. We are adding 1 neutrino, so we have 1 extra mass scale. We have 3 mixing angles, and in principle 2 CP violating phases. And well, it turns out that there is a resonance, and this was also mentioned by Juan Pablo when he discussed this problem. The resonance happens at energies about few TeV, because here we are talking about masses of about 1 electron volt. If you remember that there is in atmospheric neutrinos, there is also a resonance just from a standard 3 neutrino picture at the energies about a few GeV, which is a resonance driven by θ13 and the delta M square atmospheric and delta MEV square atmospheric is of the order of a few times 10 to the minus 3, and that resonance happened at GeV, so it's natural if we go 3 orders of magnitude in delta MEV square, we go 3 orders of magnitude in the mass. The only difference with the standard, the only difference from this case to with the standard 3 neutrino scenario that we know exists, because we know theta 1,3 is different from 0, so that resonant effect is there, and this is why, for instance, detectors like Pingu or Orca, this is a win or win situation once we know theta 1,3. The difference with the standard case, as I said, is that in the standard situation, this resonance, theta 1,3 driven resonance of atmospheric neutrinos in the GeV range, it is resonant in the neutrino mode when the mass hierarchy is normal, and is resonant in the antineutrino mode when the mass hierarchy is inverted. Here is the opposite. Here actually, the resonance, here obviously the analogous with normal inverted hierarchy is only normal, because obviously we cannot put the sterile neutrino to be the lightest, because otherwise we would have 3 neutrinos with masses of the order of 3 of 1 electron volt. So total neutrino mass would be about 3 electron volts, and we know, for instance, from cosmology that we cannot have a total mass of 3 electron volts. And so it has to be normal hierarchy within this context. But it turns out that in the case of sterile neutrinos, the resonance doesn't happen for neutrinos, but it happens for antineutrinos. And the reason for that is that, remember what Juan Pablo was discussing, that in the case of atmospheric neutrinos, here we are talking about nu mu and nu tau oscillations. In principle, nu mu and nu tau only experience neutral current effects, the neutral current interactions. And that, when you talk about 3 neutrinos, you have the nu is with charge current plus neutral current, you have the nu mu's and nu tau with only neutral current, so you can always remove a term which is proportional to the density, and you are left with only charge current with electron neutrinos, and then no effective potential for nu mu nu tau. Here, the problem is that we have sterile neutrinos which actually feel 0 potential. So what happens is that nu mu and nu tau have experienced neutral current potential, and sterile neutrinos experience 0 potential. It turns out that the neutral current potential has a sign which is different from the charge current interaction. Yes, this has to do with SU2 properties. So it turns out that the potential for neutral current, unlike what happens with the potential for charge current, has a different sign. And this is why the resonance in searches for sterile neutrinos, given that the delta MEV square has to be positive, the resonance occurs for antineutrinos, which is somehow bad, because the antineutrino flux is smaller, the antineutrino cross-section is smaller, so the effect is kind of more smeared out than if it was in the neutrino mode. Anyway, so that is how the physics go, and just a few examples of how the probabilities change. This is the survival probability for this side is antineutrinos, where you see clearly the resonance, and this is the survival probability for neutrinos. In the upper plot, I'm showing you the probability for different mixing angles. So the larger the mixing angle, the deeper the well in the resonance. The resonance is happening at a few TeV, as it should be for a mass of, this is a mass of delta MEV square of 1 electron volt square. This is how the dip changes depending on the mass, and changing the mass changes the position of the dip, and this is how we see how this goes. And this is actually different directions, how much matter the neutrinos are traversing. This is our antineutrinos. This is for neutrinos. You see there is no resonant effect here. It's just an overall suppression with some fast oscillations over the global suppression. And you see, this is the same kind of variation of parameters, and you see that this is much less prominent than this one. In the end, it turns out that this suppression is what really matters. So it's not that bad, as I mentioned, that the fact it's on antineutrinos, because actually in a detector like S-Cube, you cannot actually resolve the resonant, so this gets integrated out, and as you have a lot more neutrinos and the flux of well, not a lot, no, not a lot more, you have a few more neutrinos, and the neutrino cross section is a factor of a few larger. In the end, is the neutrino suppression which dominates the sensitivity. Okay, so these two plots, I think at least Juan Pablo saw this one. This is energy as a function of cosine of the zenith angle. So this -1 here is neutrinos crossing the entire Earth, and this is just for horizontal neutrinos, just perpendicular to the detector, just barely crossing any Earth. And this is energy, reconstructed energy, and this is reconstructed direction. This is for neutrinos, this is for antineutrinos. Clearly you see that for neutrinos, you see that this, I don't know if you can appreciate it from the distance, you see like these wavy features here, which are those fast oscillations that happen because of the presence of the extra neutrino, extra electron volt neutrino. And in the antineutrino mode, you clearly see that there is a resonance, and that obviously depends on, so the intensity of the resonance depends on how much Earth the neutrino goes through. And you see this part here, blue is zero probability, this is disappearance probability, so survival probability, and zero, this is zero for blue, and this is closest to 1, and this has to do with absorption in the Earth. These are energies of about 10 TeV, and the Earth for neutrinos with energies about 10 TeV is not transparent anymore. So anything that we do below 10 TeV, we can do just using oscillations, and we can't forget about, let's say, second order processes. Oscillations depend on the amplitude of the Fourier scattering. But then we have an next order effect, which is the absorption, which goes with the square of the amplitude. And this is okay for low energies, but as we go to high energies, this second order effect, which has to do with the absorption, plays an important role, and one has to actually take into account that in order to compute things correctly. So neutrinos are absorbed at energies about 10 TeV or so. So this has nothing to do with oscillations. Actually, oscillations are very suppressed at very high energies. Then this is for neutrinos at high energies. Then we have here neutrinos at low energies, say below 100 GeV. In this case, there is no sensitivity to large delta M squares. Yes, you see that the effect, this is with no sterile neutrino, and this is with a sterile neutrino of mass square difference of 1 electron volt square. And you see, remember that the effect on the oscillation was a very fast oscillation, so over the no sterile neutrino case, and this is what you see here compared to here. Here there is a wavy structure. You don't see it, so you don't see it. The detector is even worse at seeing it. So basically, what you see in the detector, no matter what the delta M square, is just an overall suppression. So there is no sensitivity at these energies on the mass square difference. And these plots are, again, Juan Pablo saw them, and they set bounds on the mu4, the mixture of the mu neutrino with the fourth neutrino. Remember, this is in the case of LSND, the two important mixing matrix elements were UE4 and U mu4. Here, the important elements are U mu4 and U tau 4. So there is some complementarity, but there are actually ways to escape, to make things compatible among themselves. So actually, they could be. So anyway, this is for high energies, about 100 GeV, where basically this was a search using about, I think it's 20,000 events between a few hundred GeVs and about 20 TeVs. These are through-going muons, and the main sensitivity comes from neutrinos of the order of TeV, as one could expect. Then we have the searches at below 100 GeV from IceCube, and again, it sets bounds on the different. This is U mu4 and this is U tau 4. This is for a given delta M square. I think this was 1 electron volt square, but as I said, at lower energies there is no sensitivity to the mass square difference. Anyway, this was already shown by Juan Pablo the other day. Okay, so let me move to more exotic things. I'll try not to repeat anything, but I think it was mandatory. I mentioned.
So there are some models that favor 3+2, right?
Yeah.
So those you're not going to discuss.
No. This is just all these things are 3+1, and actually I think it's even farther than that. I think this is 3+1, and in many cases they go to the 2 neutrino approximation in order to do the analysis. I don't actually remember if IceCube analysis takes into account the full thing, but I doubt it, because you would need to put more. For instance, I think IceCube sets U tau 4 to 0, which is fine, but it's within the 2 neutrino picture. So yeah, there are 3+2 scenarios that actually, I mean, 3+1 is not bad. I mean, you can make it work globally. As I said at the beginning when I was making the introduction, globally, when you take into account short-range line, you take into account LSD mini-wound, reactors, gallium atmospheric, all experiments. The interpretation in the 3+1 scenario is slightly favored at the 2 sigma level. That doesn't mean that this is globally. That doesn't mean that among different type of experiment, the tension is stronger than that. But globally, the things go up to sigma. So actually, you don't need the you don't need an extra neutrino. If you have an extra neutrino, you get a much better fit. You can play with CP violation, but you have 2 extra neutrinos in the electron volt regime, and then you have problems with cosmology. You have 2 extra degrees of freedom in the early universe, or you could have, actually. That depends on a number of things. You need that the extra neutrino have to be thermalized in the early universe to contribute as a 2 extra degrees of freedom. In general, for these large mixins, not always, it's not a general statement what I'm saying, but in principle, these 2 neutrinos are thermalized. As I said, not always, but and if they are thermalized, 2 extra degrees of freedom cannot be accounted for with cosmology. So yeah, if you only worry about neutrino experiments, things are better. You add more parameters, you will get a better fit.
That's the only reason.
Yeah. Okay, so let us move to more strange things. This was a recent proposal, actually this summer, by a group of people, actually, all of them, well, 3 of them, very good friends of mine. And this is, there have been, for many years, this sterile neutrino business is not only interesting in the electron volt scale. Actually, the electron volt scale from the model building point of view may have some issues. This sterile neutrino business is interesting in a huge range of scale. Actually, there is the proposal of, or for many years, that the dark matter could be a KEV sterile neutrino, or that other, there is the model, the so-called new standard model by Saposnikov and collaborators, where they proposed adding just the extra neutrinos, and they could explain leptogenesis, and they could explain even in some more extreme situations, even inflation, neutrino masses, and in those cases, and dark matter with a neutrino in the KEV range. And in that model, for instance, you might have a GEV neutrino, right-handed neutrino with a mass, or mostly sterile neutrino with masses on the GEV range. So there have been systematic searches of this MEV to GEV mass neutrinos, and actually there is an experiment that actually in at CERN that is proposed to happen at CERN, which is called SHIP, which is meant to be done to search for neutrinos with these masses. And there are very strong limits from different type of searches, from pion searches, pion decays, kaon decays, from actually many different type of searches, and there are very strong limits on the electron mu sectors, because that is what is easy actually to search for. And actually there is this paper, like it's about 8 years ago, that basically compiled all limits that were on the mixing. This is the mixing on electron neutrino with the 4th electron flavor with the 4th neutrino, and this is the muon flavor with the 4th neutrino, and this is as a mass of the neutrino, and this is in GeV, and this goes from basically 10 MEV to 100 GeV, and you see this number that for sure you cannot see, and I think I don't even see it myself. So this should be out of the order of 10 to the minus 5, 10 to the minus 6. So similar here. So the mixing with electron or muon flavor are very strongly suppressed just because of the searches, but it turns out that we don't have so much data from with mixing with the tau flavor. And this is what these people proposed this summer. They said, okay, remember in Juan Pablo's talk when he was discussing about the different topologies in ice cube, that there were basically muon tracks produced mainly from muon neutrinos, and there were showers which were produced by electron neutrinos or neutral current events. And then there was the possibility, if we are lucky, to see a third type of topology which has to do with nu taus. So nu tau charge current interactions comes into the detector, hits a nucleus of the ice, and then produces a neutral current shower, hadronic shower, and then produces a tau. If the tau has energy enough, it will travel far enough so that the detector can distinguish what the shower produced after the tau decays. So that a tau with a 1 PeV travels about 50 meters. So it could be that the neutrino comes in, produces a hadronic shower from the first interaction, the tau goes off after few tens of meters, decays. Most of the time the tau decays in, two-thirds of the time the tau decays into a hadronic shower. Then there is a fraction of time that it will decay into electrons or into muons. And that is what is called double bang. And that is the way one could try to distinguish taus in astrophysical neutrino searches. So this case is completely analogous to that, but in a completely different context. So here the neutrino comes in, it hits a nucleus of the detector, and due to mixing with this heavy state, produces a heavy neutrino. If this heavy neutrino lives long enough, it will decay after some time, and if it decays, let's say, tens of meters, of 100 meters, it will produce a double bang at lower energies. So the cross-section for this process obviously scales with the mixing angle square times the standard model neutral current cross-section, and in that way one can set bounds. These are the analogous plots to these ones. So these are the only limits that we have so far from Tram and Delphi. And these are mixings are of the order of 10 to the minus 2, 10 to the minus 3, peaks at 10 to the minus 4. But you have this window between few hundred MEV and few GeV, but an order of magnitude where we have no bound. And actually this is right the place where ice cube could be setting the much stronger bounds that we have currently. So, and this is just set, this region is just set because the lifetime of this neutrino, which is what sets the distance that this heavy neutrino will travel in the detector so that the double bang can be distinguished, is proportional to the, it depends on the mass and the mixing. So given a mass, a value of the mass and a value of the mixing, the lifetime of the heavy neutrino is uniquely determined, and then the distance traveled by this neutrino is determined. So by imposing a minimum distance through travel, you can set this limit with current data. Okay, so this was all about sterile neutrinos and family. Juan this morning mentioned the possibility to use neutrino experiments to search for non-standard interactions, which are driven by new terms, interaction terms in the Lagrangian. When we could have, we know that the standard model Lagrangian is not the ultimate Lagrangian, so we might have extra operators in the Lagrangian, and we should have, and some of those could contribute to neutrino interactions in different ways. So we can have modifications of the charge current interaction on neutrinos, or we can have modification of the neutral current interaction. Actually, I'm going to talk in what follows about the modification of neutral current interactions, or basically modification of how the neutrinos propagate through matter. Modification of the charge current interactions basically modify the production and detection process, but not the propagation process. So basically, what we do is we have the standard matter potential for neutrinos, 3 neutrinos traveling through matter, and we have here the electron potential. As I mentioned before, actually we would have the neutral current potential that would appear in the 3 flavors, so we can just subtract that term which is proportional to unity. And then we can parameterize the extra contribution from these extra operators in this way, in a completely generic matrix element, and that should come from new physics. And the idea is to see if we can constrain this, or if we measure some deviation that could be explained by that, what that would be telling us about the new physics or the new operators that will come into play. Okay, so what we do with atmospheric neutrinos? There are all these non-standard interactions appear in basically all kind of neutrino experiments, from solar neutrinos to terrestrial neutrinos to reactor neutrinos. In all experiments, one can have non-standard interaction effects. But here I'm talking about atmospheric neutrinos. So what is the equation that one needs to solve in order to see the effect of that? So for the first, in this equation I'm neglecting what is called tau regeneration. That I think I leave it, if someone is curious about what it is, I can answer that later, but let me say that I'm neglecting tau regeneration, whatever that is. So the equation, the evolution equation, is basically given by these 3 terms. First is the oscillation. This is written in terms of the matrix, density matrix. So by completely equivalent, one can write it in terms of a Schrodinger-like equation. No problem with that. So this is the first term is the oscillations, which is what one solves in the usual problems at lower energies. Then we have a term which has to do with the absorption of the Earth. Remember I told you that neutrinos of high energies, for neutrinos of high energies, the Earth is not transferring enough. It's not transferred anymore, so one has to take into account the absorption of neutrinos in the Earth. But if neutrinos are absorbed, they are also regenerated. So we have a neutral current interaction, the neutrino comes in, collides with a nucleus of the Earth, and then the neutrino that comes out might have a different energy, and that is what is called neutral current regeneration. So one has to take into account these effects, and in principle this other effect, but for atmospheric neutrinos is not important. And if one neglects this neutral current regeneration, which is not a huge effect, it doesn't have a huge impact, one can approximately write the neutrino flux in this way. So basically you have the incoming flux times a probability which has to do with the oscillations, standard thing, and one can factor out oscillations and absorption. And absorption is just an exponential which goes with the mean free path travel in the Earth. So this is approximately correct. It's not correct. Obviously one has to solve the full thing, but to understand the physics, this is a very good approximation. And basically in what I'm discussing, and actually what in this context can be done, all NSI, non-standard interaction effects, enter the oscillation probability. So the NSI effects enter the neutral current interactions. So in principle one might wonder why not here? Yeah, they are also here, but the corrections on the second order effect, which has to do with the absorption, are completely negligible below the percent level. So one can actually neglect all NSI effects here that are not detectable. And again, so all NSI, new physics effect, come into the oscillation probability. Okay, so one can try to see, add these terms into the Hamiltonian, and try to see what we can say. For atmospheric neutrinos, again, basically we are dominated by nu mu and nu tau oscillations, so we can reduce the problem, at least to get an idea of what's going on, into a 2 neutrino problem with constant density, and one can write this with this potential, which is similar to the potential with electrons, apart from overall factor order 1. And then one can parameterize the mixing matrix, in this case 2 by 2, by these two terms, E mu tau, which is the off diagonal, and E prime, which is basically the difference of E tau tau, epsilon tau tau minus epsilon mu mu. So it's just, again, taking off one term which is proportional to the diagonal. So with this parameterization, there is a resonance for antineutrinos when this E mu tau is positive, and when we are far from the resonant, the oscillatory pattern shifts. And the phase of oscillations is given by these two terms. So when we are far from the resonance, basically when we go, this term, for instance, for antineutrinos, this would be a negative. So we need to go to energies smaller so that the phases are similar, and this is what we see here. Where is the antineutrino thing? Actually, yeah. The blue one is without NSIs, and the red one is with NSI. You see, it shifts to lower energies. And the opposite happens with neutrinos. Blue one is no NSI, and the red is with NSI. It shifts to higher energies. It turns out that, as I said before, here there is a resonant behavior for antineutrinos, and this you see here, the red one, and this is the resonant behavior for antineutrinos, and that has important consequences actually, and you will see now. So this is basically a plot of the oscillation, what basically factor out oscillations and absorption, and I don't know if I'm going to explain this one, otherwise I will run out of time. So this is only taking into account oscillation, so basically factoring out all the other effects. So this is the flux with NSI at the detector divided by the flux of NSI without NSIs at the detector. So you see that as we go to high energies, the probability is dominated. We go to high energies, this term goes, and we are left with this term which is independent of the energy. So basically we go to high energies, and there is basically an overall suppression of the flux, no matter if we are talking about neutrinos or antineutrinos. This is solid lines are for neutrinos, dashed lines for antineutrinos. We go to high energies, there is an overall suppression, and the suppression is larger, the larger E mu tau is. But you see that when we go to lower energies, and this has to do with this crossing here, it can be that for antineutrinos, due to a resonant effect, you have a larger probability, larger flux in the case of NSI than in the standard case. So this is what one can search for with low energy, below 100 GeV or so, a few hundred GeV neutrinos, and actually this is kind of the same thing, but in adding the extra dimension of the direction of propagation, so basically the amount of Earth propagated, and this is oscillation plus absorption, analogous to the other case, and this is when we only take into account oscillations. This part again, you see, you can clearly see, if here is oscillation plus absorption, and this is only oscillations, this is all the effect of absorption. High energies, neutrinos are absorbed, nothing to do with non-standard interactions. Non-standard interactions, you see you have here now overall suppression, and you have here this interplay between standard oscillations at lower energies and non-standard interaction, which is a non-trivial interplay, unlike what happens at high energies. So one can use, actually, this is a work we did using the same data used by IceCube with to search for sterile neutrinos. So these are 1 year of through muons with energies between few hundred GeV and about 20 TeV. These are about 20,145 events, 1 year. And this is what we got with the epsilon prime and epsilon mu tau, and we got a constraint on this parameter at the level of few times 10 to the minus 3, which is the best limit on this parameter so far, improving previous limits from for instance, super K. And this is what we saw. This is the, I think is the 90 and 95%, if I remember correctly, confidence level. But you see that these dashed lines, forget about the red, I don't want to get into the discussion, the red, but you see the dashed black lines, that is a forecast we did, because this is the analysis with 1 year. IceCube actually in ICRC this year presented results of, I think it's 8 years, Juan Pablo can correct me, 8 years of through muons. So we did actually a forecast, but this forecast can be the real data, the real analysis if if the IceCube uses those 8 years. And this is what one can do with data that we have now. And this is what we show. This is the black line here, is just this range here. So it improves by, it turns what is 95 to 90% confidence level. But an interesting fact is that if there are non-standard interactions at the level close to the present bound, say few times 10 to the minus 3, with this 10-year forecast that we did, and as I said, we have 8 years of data right now, and we assume that we have that, what this data can tell us is actually it can be many sigma away from E epsilon mu tau equal to 0. So with the data we have, if there are non-standard interactions at the very close to the current limits, IceCube can already tell at many sigmas that can discover the non-standard interactions at many sigma. Okay, and actually, like a couple of months ago, IceCube did an analysis of NSI with lower energy neutrinos, even lower at the 100 GeV range or so, and this is the red lines are the limit obtained by IceCube with lower energy neutrinos. The green lines are the ones that we obtained using their data. So once everything is combined, I presume that one can improve significantly these bounds. And actually, remember, this green line is with only 1 year. They have a factor of 8 more. Okay, and this is the only slide on high energy neutrinos in this talk, but
In the previous slide, so I mean, what's the difference between why we to the right you got a larger difference?
what do you mean? That they are not symmetric?
Yes.
Well, there are effects which are. I mean, I'm simplifying the discussion, and in the actually at high energies, the sign of E mu tau is very difficult to distinguish. But at low energies, when we go to low energies, there is an interplay with these things. And actually it's more complicated, because I'm even simplifying already in the limiting case of about 100 GeV. At low energy, you have an interplay of these guys when in the sign. This is already when the phase is small. But there is a much non-trivial interplay, and you can tell the difference between the signs. And this is why these bounds, our bounds are not that different. You see, are very close, are very symmetric, but the low energies, it's not symmetric at all. And this is why. Actually, the IceCube, the red one, the red line should is to be make a fair comparison. Should be compared with the blue line, which is this is the limit obtained by super K in with a set of events in a range very close to what the IceCube. The IceCube, the red lines here are using neutrinos within this range, which is very similar to the range used by super K. So this is the improvement that can be done with IceCube, and then IceCube can also make this limit, but this is in a different energy range. Okay, so, and these non-standard interactions, remember the discussion I had yesterday about the flavor composition and different ways of affecting the flavor composition at the detector, and actually also non-standard interactions can affect the flavor composition, because the non-standard interactions change the probabilities of nu mu's to nu taus and so, and could affect the flavor composition. There is a small effect if the flux that arrives to Earth is produced in the standard 1, 2, 0. That means like pion decays, 1 electron neutrino per 2 mu neutrinos and 0 tau neutrinos. In that case, the differences are small. These are different, let's say, angular directions, different amount of propagation, amount of matter propagated through. But if the composition is not that standard, and this could be, for instance, neutron decays, the effects of non-standard interactions due to the propagation through the Earth of the flux that arrives to the Earth, so these are for through-going neutrinos, would be a significant, could have a significant effect. Okay, just that comment. So, but one can also search for completely non-standard oscillation terms. That could be, for instance, coming from violation of equivalence principle, or violation of Lorentz invariance, or crazy stuff. That one is like what Andrea was discussing today about the decay of electrons. So no one expects this, but one should look for these things in case occurs. And for instance, in the case of Lorentz invariance violation, we have operators of that kind, even operators, and that are proportional to the energy. And these different energy dependence of the propagation of neutrinos would affect the results. And actually this was discussed in some length by a paper like 12 years ago by Gonzalo Garcia, Halsen, and Michele Maltoni. And they study how all these new terms would affect the observations. And actually they made this prediction, you don't need to get into the details, right? Just they got this prediction of what is the excluded region that they could get. And well, if you could read that, this prediction 12 years ago is not that far from the results that were obtained, were presented a couple of months ago by the IceCube collaboration using their low energy data. So yeah, this is the exclusion on this parameter that had to do with basically this is a matrix. This C4 is a matrix, 2 by 2 or 3 by 3 matrix, and this is just a combination of diagonal and non-diagonal and diagonal terms. Actually, this is not the best. These are not the best limits on this kind of extra terms, but one can think of more complicated operators. They mentioned 6, 7, 8 that could come from whatever new physics scenarios, and actually all these operators, the best limits are obtained with the current IceCube data. Okay, more stuff. So we have TRIDENT production can be searched for. This is a standard model process. So this is a neutrino coming in, hitting a nucleus, and then you have the photon field of the nucleus, and then this photon splits into 2 leptons. The 2 leptons, then you have this neutrino produces a lepton, and you have a W propagator here, and that hits the lepton split from the photon, and that produces a neutrino. So basically you have a neutrino coming in, hitting a nucleus, and producing 2 leptons and 1 neutrino. So basically this signal, and this is pure standard model. This process exists in the standard model. And the signal is a dimuon signal. For instance, you produce new mu here, you will produce a muon, 2 muons, basically collinear. And that is kind of, should be relatively easy to see. And these people, I think this was early this year or late last year, they computed what is the rate of these events in detectors like Pingu or Orca, which are low energy versions of IceCube or Kilometer CubeNet, and they computed that they would expect few events per year. Know that the cross-section of the TRIDENT production, which is how this process is called, is several orders of magnitude, 6, 5 orders of magnitude, 4 orders, depending on the energy, smaller than the standard charge current interaction. So it's difficult. They only expect a few events per year, but they should be there. So let's go. This is just a standard model process. But one can use this kind of logic of this kind of process to search for new physics. Instead of exchanging standard model gauge bosons, there are new gauge bosons in the game. One can search for the same kind of diagram and put limits on the mass, or detect limits on the mass and the coupling of these new interaction terms. And this is what these people did. They considered 10 years of IceCube, and this is actually the gray area is what the IceCube could do after 10 years. And this is LHC, and actually this is G minus 2 limits, and this is the blue region is the LHC limits on this kind of process, on this kind of extra C primes. So IceCube can also help on that, on these kind of things. Then IceCube can look for magnetic monopoles. So magnetic monopoles are around since the 30s, right? Since Dirac, who hypothesized that the existence of magnetic monopoles, because that would explain the quantization of electric charge that we see. And that would imply that the magnetic charge should be proportional to the electric charge. And actually these magnetic monopoles appear in many grand unified theories with masses, in these grand unified theories with masses of the order of 10 to the 17 GeV or so, which are the scale of grand unification. But also there are many models that could also, in which they could also appear with much smaller masses. And actually magnetic monopoles can be accelerated by galactic magnetic fields to very high energies. So these magnetic monopoles can be depending on the mass, obviously, and that depends on the theory that predicts those, can be relativistic. And they can be searched for in neutrino telescopes. So the signature is very similar as a high energy muon. The difference is that given that the magnetic charge goes like that, so it's much larger than the electric charge, this is alpha 1/137, it means that the photon yields from Cherenkov light is about almost 4 orders of magnitude larger than what a muon the Cherenkov light from a muon would be. So that could be used to search for these magnetic monopoles. There are some technical issues but for instance, we know a muon with a few hundred GeVs loses energy constantly. So the energy losses, the dx of the muon of a few hundred GeV up to close to TeV, 600-700 GeV or so, is basically constant. If we were to see a magnetic monopole that with a loss which is about 9,000 times, with an amount of photons, Cherenkov photons, which is about 9,000 times, we could confuse that magnetic monopoles with a muon, but with much higher energy. But if a muon had a much higher energy, we would expect that the energy losses would be not constant, but would be growing with the energy. So there are ways to distinguish the muon from the magnetic monopoles, and Juan Pablo or other experimental colleagues can explain you a little bit more in detail these things. And that this can be used to constrain ranges of velocities. This is velocity of magnetic monopoles. For those magnetic monopoles, this is the emission, the number of photons, Cherenkov photons emitted by a magnetic monopole with a given velocity, and this is the number of photons emitted by a muon with the same velocity. So in a the water Cherenkov detector, ice Cherenkov detector, any particle with a velocity something like about 0.74 the speed of light would emit Cherenkov light. So one can search for those monopoles in this region, but also it could be that these monopoles are below Cherenkov threshold, but they are energetic enough, so let's say 0.5 or 0.6, that they can knock off electrons from the nucleus. So, and those electrons could be very relativistic and emit Cherenkov light. So also, even if magnetic monopoles are non-relativistic, they can be searched for in neutrino telescopes. And actually, these are the limits from the flux upper limit as a function of the velocity of the monopoles. These are the blue is the ice cube limit, and the red is Antares limit. And actually, I learned recently that it was I think in ICRC that ice cube is also investigating the possibility to use luminescence to detect the luminescence in such a way that they could be sensitive to even lower velocities of magnetic monopoles. So in that case, the magnetic monopole would not be energetic enough to knock off the electron, but would be energetic enough to make the electron to jump to a different level, and just that would emit radioluminescence, like basically the lamps in the street, or like phosphorescence light. And well, that's kind of interesting. Anyway, let me move on. I don't know how much time do I have. How much? Few minutes.
5 minutes.
Okay, so I will go fast over this. So then obviously one can search for dark matter, and there are many ways to search for dark matter with neutrino telescopes. I discussed the other day the high energy range of where one can search for PEV dark matter, but actually one can use neutrino telescope to search for more or less standard WIMPs. And there are many different places where one can look at the annihilations of these WIMPs into neutrinos. And one can search for annihilation, and here we have the particle physics ingredients that enter, and the astrophysical part, and one can search for decay, which is basically what I discussed the other day. The main differences, apart from the fact that annihilation depends on the cross-section and on the mass square, and the decay depends on the lifetime. The main differences here are the dependence on the density of the of the region we are looking at. For instance, if we search for dark matter annihilations or decays from the galactic center, we need to know what is the density profile of the dark matter in our galaxy. In the case of annihilations, as we need two particles to annihilate, the density goes as the density, the flux or the rate of annihilations goes as the density squared. In the case of decays, we only need one particle to decay. The flux goes as linear with the density. And that is very important because we know that the density profile in the galaxy is more or less peaked towards the center, so that implies an enhancement towards the center. So this enhances the signal. A dependence on the square enhances the signal. Anyway, so there are many uncertainties in these searches. We don't know exactly how the profile looks like, if it is more cored or if it is more cusped. There are uncertainties in the local density. There might be presence of a substructure, all the different things. There might be that, for instance, the halos are not spherical, as usually assumed, that actually halos are not spherical in general. Simulations don't find spherical halos in general. They are like ellipsoids. And we did actually we studied that a few years ago, and actually we know that the fact that halos are non-spherical could have an impact on the determination of the local density at the level of 20-30%, but it's not that important on the J factor. J factor is basically this thing. So the effect on the J factor for gamma rays or neutrino searches is at the level of 10% or smaller. So the uncertainties coming from the uncertainty of what is actually the density profile are larger than the uncertainties coming from the non-sphericity of halos. Anyway, so these are, one can search for neutrinos coming from different places, like the galactic center or galaxy clusters, and one can model the dark matter content on those systems and try to estimate what is the flux of neutrinos for different cases one would expect, and one can set limits, and these are limits from IceCube of different type of searches using different type of lengths, tracks, showers. These are limits from Antares. Antares is a little bit better in this regard because they are in the north hemisphere, so they have the south hemisphere, the galactic center is on the south hemisphere, so all the muons that all the through-going muons, they can search for dark matter using through-going muons, which have a cleaner way to distinguish the background. And anyway, so they can get slightly better limits. So there are also, as I mentioned, there are, for instance, then our ignorance of the profile brings order of magnitude uncertainty on the final limits, different channels, annihilation channels into different particles, as I mentioned the other day, also produce different amounts of flux of neutrinos and gives rise to different bounds. Anyway, then there is also another possible signal, which is the cosmic diffuse signal, and in this case we have this term, which is basically this rho square integral, but here we have to integrate all halos of all masses at all redshifts. So this is this integral. But this integral depends also on the number of halos that we have at all redshifts and for all masses. Obviously this has some uncertainties. The density distribution of different halos of different redshifts with different masses have an uncertainty. This can only be obtained in to great extent by numerical simulations. We did a work with one of my students and Alejandro Ibarra a couple of years ago to try to evaluate what are the uncertainties on this kind of flux, and it's within an order of magnitude. I think that would be a fair estimate of what the uncertainties on this kind of flux are. We computed what is the reach of neutrino detectors using through-going muons and using cascades, and it turns out that even if through-going muons point to the source, it turns out that, for instance, in this kind of searches, this is a cosmic diffuse signal, so it's a signal that comes from all directions. In this case, it's not that important what is the direction of the source, because it's coming from the entire sky, and in that case, it's much better to look for cascades for which the background is much smaller. Remember the new muon, new EV ratio of atmospheric neutrino fluxes? I told you that was growing with energy, so there are much more new muons than new E's, so that helps when we don't care about the directionality of the source to discriminate much better a possible signal. And in the last couple of minutes, there are other type of signals, which is when dark matter accumulates in the sun, and these are unique signatures that only happen or could happen in neutrino detectors. How this goes is that we have a halo dark matter that surrounds us, and these dark matter particles are hitting us and are hitting the sun, and eventually when a dark matter particle of the halo hits the particles of the sun, can get to a velocity which is smaller than the escape velocity of the sun and get into a closed orbit. This particle would eventually interact again with the particles in the sun and get to a smaller and smaller velocity, and eventually will get trapped in the sun, and then multiple scatterings in the sun will get all those dark matter particles trapped by the sun into a thermal distribution. But those particles that are accumulated in the sun could eventually annihilate. So the capture rate, which is the rate in which these particles are captured, depends obviously on the amount of dark matter particles that are in the halo, the local density, but it depends on the velocity, and it depends on the scattering cross-section. But this scattering cross-section is exactly the same cross-section that is searched for in direct detection experiments. So this is the capture rate. But as I said, these particles can eventually annihilate and would annihilate and produce pairs of quarks, or pairs of muons, or pairs of taus. And in general, when we search for that, and I mentioned that several times, that it produces a flux of neutrinos, but it will produce a flux of gamma rays. And so, in the case of the sun, nothing else but neutrinos can escape. So, photons that are produced would be completely reabsorbed in the sun. So the only particles that can escape the sun are neutrinos. So the only way to search for these annihilations is using neutrinos, and one can compute what is the annihilation rate one would expect, and try to see if one can detect neutrinos coming from the sun with energies in the GeV range. And I won't explain that because I don't have time, so these are just basically the evolution equation, the dependence, capture rate, annihilation rate, and something which is called evaporation rate that I won't discuss. And these are the different ingredients, different cross-sections. The spin-independent cross-section is a coherent interaction, and it goes as the atomic mass to the fourth power, and spin-dependent, that goes as atomic mass as the second power. This is like in direct detection experiment, and this is why the limits for a spin-independent are always much better than in the case of a spin-dependent. The propagation has to take into account also the absorption of neutrinos in the sun, a number of things. And well, this is an estimate we did using deep core, how far one can get for low mass WIMPs on the spin-dependent cross-section. This is, we assume, a systematic error of 15%. This is with no systematic error, so this is kind of the ultimate sensitivity for deep core. And obviously, there are many telescopes looking for that. We have IceCube that presented a few last year or so, a couple of years ago, maybe not last year, results, and TIRES with 5 years, Super K, and Baxan that is much smaller, but have 24 years of data. And here you have the data. This is spin dependent, and actually spin dependent with neutrinos. You see Super K, and you see IceCube here, and these purple here are PICO. So these are direct searches, and so far limits coming from neutrinos, from dark matter annihilation in the sun, are the ones that dominate the spin-dependent limits. Then we go to spin-independent. We can also search for neutrinos from the sun, but in this case, direct detection searches dominate. These are the limits for neutrinos from the sun, and these are direct detection searches. And well, actually, this is all taking into account interaction with nucleons, but actually dark matter could be interacting with electrons. And it turns out that the fact that the mass of the target, the electrons, instead of the nucleons, makes has a crucial impact. In the case of interaction with nucleons, one doesn't have to care about the thermal motion of the nucleons, so one can take the nucleons as temperatureless, so completely at rest. In the case of when the targets are electrons, the thermal motion is critical, and actually can increase the capture rate several orders of magnitude. And this is what I work out with my student. Actually, he just finished. He's not a student anymore. Yeah, it's about 3 orders of magnitude effect depending on the type of interaction. And actually we evaluated the fluxes, and actually in some cases actually dark matter electron could be even more important than dark matter nucleon, and this is something we are working on now in probably next month or so. And I don't know if you want to know, secluded dark matter. This is just dark matter which contains secluded from standard model particle by a long-lived mediator. And in that case, the dark matter annihilates in the sun, but it annihilates into this mediator, but this mediator interacts very little with the standard model particles and can leave the sun and then decay close to the detector. And in that way, for instance, one can test models with very high dark matter masses for which standard neutrinos would be absorbed. So, for instance, we have a TeV or 10 TeV dark matter mass and produces annihilates inside the sun, the neutrinos which have energies comparable to the mass will be greatly absorbed by the sun. In this kind of a scenario, the mediator just leaves the sun and then decays into these high energy neutrinos that can be searched for, and the limits can be more constraining. Anyway, just to finish. So there are very large statistics with the neutrino telescopes given by the atmospheric neutrino fluxes, and there's a huge range of energies and baselines, and one can play many different games. And in addition to perform standard analysis, like we've heard about, the atmospheric neutrino flux could be used to search for features and from new physics, or could be actually the background for new sources of neutrinos, like in these all these dark matter searches. Thank you.
So we have time for 1 or 2 questions. Something?
It's not a question.
It's more like a comment and clarification. So on the spin-dependent limits, the our 2017 limits are about 2 orders of magnitude below pico 12. So at 10 to 50 GeV, we are better than super K and
10 to
lower.
Here?
Yeah. So that should it goes.
This is last year.
Yeah, the 2017. The leading now.
It's somewhere here.
It's it's below.
Below here?
Yeah.
Okay.
At between 10 and 50. So for the first time, direct detection.
Okay.
At least in that.
Yeah. Okay. Thanks. I haven't checked the current comparison, but
Yeah,
thank you.
but
Thank you. Yeah. Nice.
Another question. Come on, don't be shy.
So in your favorite WIMP model, since you have this calculation of how much of the WIMPs are trapped in the sun, so what is the fraction of the mass of the sun then that is?
What is it? What? Sorry?
The fraction of the mass of the sun, which is WIMPs in your favorite model.
No, it's very little. Very little. Let me see if I remember the number of. One has to sit and do the number, but the number of dark matter particles that can get trapped in the sun is of the order of 10 to the 50 or something like that. But one has to make the numbers.
Why is it so small?
It's very small.
If most of the matter is dark, how come so little gets trapped in the sun?
If most of the matter
In the universe, right? Factor 5 relative to baryonic.
No, I mean, it depends. I mean, the amount of matter of particles that are trapped by the sun depend on the mass of the particles. Obviously, the higher the mass, the less likely they are trapped. And actually, the capture rate goes as 1 over the mass square. So yeah, it's more difficult. So that this dependence is explained the following way: one power of the mass has to do with the same as what Andrea was mentioning in the talk. The same reason why this is a line here, just because the number density of particles goes as 1 over the mass. That is one factor. And the other factor is just kinematics. It's just less likely than a particle with a high mass hits a nucleus very light and goes below escape velocity. So that is an extra factor. So yeah, the higher the mass of the particle, the less likely they can get captured. But yet, even in the most likely situation, the amount of matter that can get trapped in the sun is completely ridiculous. You will need a huge, completely excluded cross-section in order to have any impact on the dynamics of the sun. That doesn't mean that this kind of processes cannot be searched for in other stars. And actually, if you go to places where there is a lot of dark matter, like close to the center of the galaxy, which you have densities like million, 10 to the 7 times larger than here, then the cross-section that you will need to affect the dynamics, the evolution of the stars, will be much lower, close to what currently is within the limits. The problem with that is that you have to search for stars in the center of the galaxy. So to distinguish stars which have an uncommon behavior in a place which is full of stuff is very difficult. But in the sun, with the local density of dark matter we have, with the cross-sections that we know cannot be more than something, there is no way we modify the dynamics of the sun. It's true that without modifying the dynamics of the sun, in some range of the parameter space, you can slightly modify the flux of neutrinos coming from the sun. So you can also use the solar neutrino fluxes to bound this kind of physics. So there are a number of ways, but the number of particles in the sun is very, very small.
So this modification of the flux would just be an overall change, or would you also change?
No, it changes shapes too, because it changes temperature. So it changes basically the temperature of the sun.
Thank you.
Are there any other questions?
If I may continue on this is interesting. It's the first time I hear this. So the mechanism by which neutrino emission from the sun would occur is through a change in the temperature of the sun. Is that what you just said?
Yeah. So you change slightly the temperature of the medium, and that would change slightly the fluxes.
But I thought the temperature was pretty constrained by existing data already, and
yeah.
luminosity constraint is extremely constraining, right?
It is, but still there are some very small effects. But
is it fair to say that maybe the biggest effects are in the B8 flux, which is possibly the one that is more changed by tiny?
I think that's correct. I think if I remember correctly, there are a number of people working on that. Are basically two people. One is Elidio Lopez from Portugal, and the other one is Joe Silk, that probably you well know, famous cosmologist. And these people have a number of papers on studying what is the effect of dark matter on the neutrino fluxes. So, and this is, if I remember correctly, those are more, yeah.
Okay, no more questions, right? No, if you have questions, you are welcome.
Not so well.
only a little bit welcome.
You are welcome. If not, we have a very short coffee, 15 minutes, because we are delayed.